Hi, hello. For this video, we will be discussing angle modulation transmission. Okay, so we're done with amplitude modulation. The next type of analog modulation that we have is angle modulation. Okay, so what do we mean by angle modulation? Okay, so just for a review, our analog signal has three properties that we can alter. Okay, so that means these are the three properties that can be varied or that can be modulated. So we have the amplitude, we have the frequency, and we have the phase. Okay, so the first property is the amplitude. So when we vary the amplitude of your carrier in accordance with your modulating signal, so we have the amplitude modulation, and then we have the angle modulation. So our angle is the we have two types under angle modulation. So we have the frequency and we have the phase. So we can alter the frequency of your analog signal. Likewise, we can change the phase of your analog signal. So if we do that, we are having frequency modulation and we have phase modulation. So frequency and phase are both under angle modulation. So therefore, we have here FM and PM. So but often they are referred to as simply FM, okay, although there are actual distinctions or differences between the two. We have here angle modulation versus amplitude modulation. So as you can see, we have more advantages of the angle modulation compared to the disadvantages. Okay, so angle modulation was first introduced in 1931, okay, so as an alternative to amplitude modulation. We have here several advantages. Number one, noise immunity. So since noise can be categorized as changes in the amplitude, so when we do amplitude modulation, AM is more prone to noises compared to the angle modulation. So that is the first advantage of angle modulation. So noise immunity, noise performance, and signal to noise improvement. Then we have what we call the capture effect and the power utilization and efficiency. So those are the different advantages. Okay, so however, we have these two main disadvantage of angle modulation. First is the bandwidth. So angle modulation requires more bandwidth compared with the amplitude modulation, and circuit complexity and cost. So the circuits, okay, so the circuits that are involved in angle modulations are more complex, therefore they are more expensive compared with the angle modulation. Okay, so but as you can see, there are more advantages compared with the disadvantages. Okay, so angle modulation was first introduced in 1931. Okay, this is an alternative to amplitude modulation. This is less susceptible to noise than AM, and consequently, it improved the performance of radio communications. So it was Major Edward Howard Armstrong in 1936. Okay, so he developed, or he invented, the super heterodyne receiver. Okay, so in 1936 was the first successful FM radio system, and in 1939, July of 1939, at Alpine, New Jersey, was the first regularly scheduled broadcasting of FM signals. Okay, so usually here in the Philippines, when you wanted to listen to news like that, so we usually make use of amplitude modulation. But when you wanted to hear music, listen to music, so that is your FM radio stations that you are listening to. So that is your frequency modulation. Okay, so in 1939 was the first regularly scheduled broadcasting of FM signals. So we have here commercial radio broadcasting, and also the television sound when we transmit TV signals, usually they are divided into two, the audio and the video. So usually the video make use of amplitude modulation, while the audio of the TV signals are in the form of frequency modulation or FM. Okay, so this is also used in two-way mobile radio, cellular radio, microwave, and satellite communication systems. So as you can see, if we're going to look at the spectrum of frequency spectra, usually the applications, these applications that you have here, that you can see here, are usually they fall under the frequency of FM. Okay, so the frequency modulation falls between 88 to 108 megahertz. Okay, so for angle modulation, again, we have an equation. This is our equation for our sinusoid. Okay, so we have an amplitude and we have the frequency and the phase. Okay, so this is our frequency and we have here our phase. So every time you vary the phase and the frequency, we call that as angle modulation. Okay, so in AM, we usually vary the amplitude. So this is the amplitude of your sinusoidal wave. So when we vary, okay, so this is the peak carrier amplitude voltage. So this is your this is the equation of your angle modulated wave. So this VC is the peak carrier amplitude, that is in terms of voltage. Omega C, that is your frequency. So this is our frequency and this is our phase. Okay, so this is our phase. They are both in radians. So although frequency can be also expressed as hertz. Okay, so this is our equation for angle modulation. This time our amplitude is being held constant while we only vary the phase angle. So with angle modulation, it is necessary that your phase, okay, this is our phase angle, be a prescribed function of your modulating signal. So in essence, the difference between FM and PM lies in which property of the carrier, okay, so either its frequency or its phase is directly varied by the modulating signal, and which properties is indirectly varied. Okay, why do we say that? Because whenever the frequency of the carrier is varied, the phase is also varied. Okay, so directly we are varying the frequency and indirectly we are varying the phase. Okay, and vice versa. When we are directly varying the phase, we are indirectly varying the frequency. So if the frequency of the carrier is varied in accordance to with the modulating signal, FM results. Okay, so when we are directly varying the frequency, so FM results. So if the phase of the carrier is varied directly in accordance with the modulating signal, PM results, or phase modulation results. Therefore, direct FM is indirect PM, while direct PM is indirect FM. Okay, so you have to remember that. So this is our second equation. Okay, so our phase or theta t, okay, or our phase angle is equivalent to F, function of the amplitude. So this is the modulating signal Vm with respect to time. Okay, so Wm is our angular velocity of the modulating signal, that is given in radian per second, or that is in terms of hertz, it is also given as 2 pi Fm, wherein Fm is our modulating signal frequency, that is in terms of hertz. Vm, that is our peak amplitude of the modulating signal voltage. The difference between FM and PM, as I've mentioned a while ago, lies in which property of the carrier is directly varied by the modulating signal. Okay, so when we say direct FM, varying the frequency of the constant amplitude carrier directly proportional to the amplitude of the modulating signal at a rate equal to the frequency of the modulating signal. While direct PM, or direct phase modulation, is varying the phase of a constant amplitude carrier directly proportional to the amplitude of the modulating signal at a rate equal to the frequency of the modulating signal. Okay, so I'll repeat, direct FM means indirect PM, while direct PM means indirect FM. Okay, so the figure shows how the carrier frequency FC, okay, so how the carrier frequency FC is changed when acted on by a modulating signal. So this is our modulating signal. Okay, so we have here delta F. Delta F stands for frequency shift. Okay, so how your frequency changes with respect, how your carrier changes with respect to your modulating signal. So it is what we call the frequency shift. So we have here the magnitude and direction of the frequency shift is proportional to the amplitude and polarity of the modulating signal. Okay, VM. So the modulating signal VM and the rate at which the frequency changes are occurring is equal to the frequency of the modulating signal. So it is very important to note the amplitude. So this is the amplitude of your modulating signal, the magnitude of your modulating signal, and the frequency. This is your FM. This is the frequency of your modulating signal. For example, a positive modulating signal produces an increase in frequency, while a negative signal produces a decrease in your frequency. Okay, so this is your positive. For example, a positive VM, that means an increase in your frequency. So this is FC plus frequency shift, and a negative. So this is our negative VM. So your negative VM produces a decrease. So therefore, we have your FC minus delta F, or the frequency shift. Okay, so the rate at which frequency changes is equal to the frequency of the modulating signal. It follows the frequency of your modulating signal. Although the opposite relationship could occur depending on the type of modulator circuit that is used. So what do we mean by that? So it means that a positive modulating signal can have a decrease in the frequency, or a negative amplitude or magnitude can have a positive or an increase in the frequency. So it depends on the type of modulator that you are going to use. Okay, so this slide shows the time domain. So the previous slide shows the frequency domain. Okay, so we just saw lines there. So in here, we can see the waveforms. So this shows the angle modulation in the time domain. Okay, the waveform for a sinusoidal carrier for which angle modulation is occurring. So let us define some symbols here. So we have delta theta. Okay, so we every time you say this, we are talking about phase deviation. Okay, so this is phase deviation. Okay, so this is the reference angular displacement of the carrier in radian in respect to the reference phase. Every time you can see delta F, this is frequency deviation. Okay, so deviation means change with respect to time. So this is a relative displacement of the carrier frequency in hertz in respect to its unmodulated value. So both your phase deviation and your frequency deviation, the magnitude is proportional to the amplitude of the modulating signal, and the rate at which the changes are occurring is equal to the modulating signal frequency. Just like in AM, your carrier is being varied in accordance to the amplitude of your modulating signal. So likewise here, the phase deviation and the frequency deviation is proportional to the amplitude of the modulating signal. Okay, so the theta, okay, the theta of the phase angle of the carrier is changing proportional to the amplitude of the modulating signal. That is your VMT. Okay, so the relative angular displacement, and we say angular displacement or the shift. Okay, so the relative angular displacement of the carrier phase in radian in respect to the reference phase is called our phase deviation. So the relative displacement of the carrier frequency in hertz in respect to its unmodulated value is also what we call the frequency deviation. This is the angle modulation in the time domain, okay? So frequency changing with respect to time. So if you're going to look at the figure, the amplitude here is constant, okay? So you cannot see any amplitude changes. So what changes is the frequency. Okay, so sometimes the frequency is the time is maximum, so minimum frequency, and sometimes your time is minimum, so that T max means minimum frequency and T min means maximum frequency. Okay, so F here is changed or deviated over a period of time. So it is the frequency that is changing. So this shows a sinusoidal in which the frequency is changed. Okay, so the fat portion of the waveform corresponds to the peak to peak change in the period of the carrier. So that is delta T. Okay, so T minimum corresponds to F maximum. Okay, so if you're going to remember the formula for F is equivalent to 1 all over T. So when your T is minimum, so you have your frequency as maximum. Or if this is maximum, so your frequency is minimum, or they are inversely proportional. Okay, so the peak-to-peak frequency deviation is determined by simply measuring the difference between the maximum and minimum frequency. So that means, class, that if we have delta F is equivalent to, or delta F peak-to-peak is equivalent to 1 all over T min minus 1 all over T max. Okay, so that is our peak-to-peak frequency deviation. Okay, so if we wanted to solve for the peak-to-peak frequency deviation. Still angle modulation in the time domain. Okay, so whenever the period of a sinusoidal carrier changes, its frequency and phase also change. And if the changes are continuous, the wave is no longer a single frequency. So we have what we call the resultant angle modulated waveform. So the resultant angle modulated waveform comprises the original unmodulated carrier frequency and an infinite number of pairs of side frequencies displayed on either side of the carrier by an integral multiple of the modulating signal frequency. So if you're going to remember in AM, okay, so in AM, we have the original or the carrier signal, okay, with two sidebands, the lower and the upper sidebands. For angle modulation, it comprised of the original unmodulated carrier, just like in AM, but the difference is it has an infinite number of pairs of sideband. So for AM, we only have one pair, the upper and the lower sideband. So in here, we have infinite pairs. So this is also the reason why FM or angle modulation requires higher bandwidth compared with FM because of the infinite number of pairs of sidebands it produces. Okay, so the original unmodulated carrier frequency is often called the carrier crest frequency. Okay, so we have here the mathematical analysis for angle modulation transmission. Okay, so the difference between FM and PM is more easily understood by defining four different terms. Okay, so so that we can easily understood those four different terms, I have written here the first equation that we have encountered in the beginning of our lecture. So that is the VC cosine omega CT theta t. So what are the four terms that I am referring to? So we have the instantaneous phase deviation, we have the instantaneous phase, instantaneous frequency deviation, and the instantaneous frequency. Okay, so let us start with the instantaneous phase. Okay, so our instantaneous phase is the precise phase of the carrier at a given instant of time. So instantaneous phase in this formula is the omega ct plus theta t. So they are in radians. Okay, so omega ct, let us elaborate omega ct. This is the carrier reference phase in terms of radians. So our omega ct is 2 pi. Okay, so that is 2 pi f. What is 2 pi f? So 2 pi is in terms of radian per cycle. Fc, that is cycles per second, although Fc is the carrier frequency, also represented as hertz, but it can also be represented as cycles per second. And then, of course, time, this is represented by seconds. So seconds will be cancelled out, cycles will be cancelled out. So what remains is radian. So this is 2 pi. Omega is also written as 2 pi f. Okay, so we place letter C here to signify that we are talking about the frequency of the carrier. Okay, so we are talking about the frequency of the carrier. So theta t is the instantaneous phase deviation, also in terms of radian. Okay, next is the instantaneous phase deviation. A while ago, we have instantaneous phase. So this time, we have the instantaneous phase deviation. So the instantaneous phase deviation is the instantaneous change in the phase of the carrier at a given instant of time and indicates how much the phase of the carrier is changing with respect to its reference phase. So in this case, class, we have here the instantaneous phase deviation is represented by our theta t, or theta t is in terms of radians. Okay, so the third is the instantaneous frequency. So instantaneous frequency is the precise frequency of the carrier at a given instant of time and is defined as the first time derivative of the instantaneous phase. Okay, so from the earlier slide, we have defined the instantaneous phase as the omega ct plus theta t. Okay, so we get the first derivative of this. So the first derivative for this is given by omega c, so with respect to time, so this is omega c, plus we have the first derivative of your theta with respect to time, and it is given by radian per second. Okay, now substituting 2 pi fc, we know that omega c means 2 pi fc. So substituting 2 pi fc, okay, for omega c, because it's with respect to time, plus the first derivative, or theta t. So we just substitute the value for omega c here. Okay, so we have here 2 pi fc plus this one. So fit now, or the instantaneous frequency, is given by the formula 2 pi fc plus theta t radian per second. So this is 2 pi radian per cycle, okay, which is equivalent to fc. So this is cancelled out. So what remains is fc, and then we have here pi omega t with divided by 2 pi s. Okay, so simplifying further, we have fc plus the first derivative of your theta t all over 2 pi. That is in terms of hertz. Okay, so since that is instantaneous frequency, so our formula, or our unit there is hertz. Okay, and lastly, we have the instantaneous frequency deviation. Okay, so what is the instantaneous frequency deviation? The instantaneous frequency deviation is the instantaneous change in the frequency of the carrier and is defined as the first time derivative of the instantaneous phase deviation. So a while ago, we have the instantaneous frequency deviation is simply theta t first derivative, or theta prime t radian per second. Okay, so the instantaneous phase deviation is your theta t, right? So theta t radian per second divided by 2 pi radian per cycle. So we have here radians will be cancelled out. Radians will be cancelled out. Okay, so the remaining is cycles per second. So therefore, the instantaneous frequency deviation is given by cycles per second, or H. So every time you see this apostrophe sign here, this means you're having the first derivative with respect to time. Okay, so those are the four important things that you have to know: the instantaneous phase deviation, the instantaneous phase, the instantaneous frequency deviation, and the instantaneous frequency. Okay, so you have to take down notes of those things. Okay, so the phase, let us now define phase modulation based on the four definitions or four terms that we have defined previously. So phase modulation can be defined as angle modulation in which the instantaneous phase deviation, so this is our instantaneous phase deviation, is proportional to the amplitude of the modulating signal, and the instantaneous phase deviation is proportional to the slope of the first derivative of the modulating signal. Okay, so how about frequency modulation? So for frequency modulation, it is also an angle modulation in which the instantaneous frequency deviation, so this one, the first derivative, is proportional to the amplitude of the modulating signal, and the instantaneous phase deviation is proportional to the integral of the modulating signal voltage. Okay, so that is our formal definition for phase modulation and frequency modulation. So for a modulating signal VMT, the phase and frequency modulation are the following. Okay, so PM, okay, or the theta t is given by kVMT, that is in terms of radian, and we have here for FM, that is the first derivative, so theta prime theta, which is equal to K1 VMT radian per second. Okay, wherein your K and K1 are constants. So K and K1 are what we call deviation sensitivities of the phase and frequency modulators respectively. So for PM, the deviation sensitivity is K, and K has a unit. So K is in terms of radian per volts. Okay, so if K is radian per volt and VM is in terms of volts, okay, so the unit for PM is radians, okay, because the voltage here and the voltage for your VM will be cancelled out, giving us a unit which is equivalent to K. While for FM, the deviation sensitivity is K1, okay, and K1 is given by hertz per volts. Okay, so hertz per volt. So if we multiply that with VM, so V will be cancelled out. So that will give us hertz. Or hertz is also represented as cycles per seconds or radian per second. Okay, so that is your K and K1. So K is for PM and K1 is for FM. So what are deviation sensitivities? So what is your K and what is your K1? So deviation sensitivities is the output versus the input transfer function for the modulators, which give the relationship between what output parameter changes in respect to specified changes in the input signal. So for frequency modulator, changes would occur in the output frequency, okay, with respect to the changes in the amplitude of the input voltage. While for phase modulator, the changes would occur in the phase, okay, so that is the difference. So for FM, the change will occur at the output frequency with respect to the changes in the amplitude of the input voltage. So for phase modulators, the changes would occur in the phase of the output frequency. So the phase of the output frequency in respect to changes in the amplitude of the input signal. Okay, so that's why their name is frequency modulation, or it is being it happens in a frequency modulator circuit or phase modulator. So phase is changing and it occurs in a phase modulator circuit. Okay, so deviation sensitivity, let us define again. So we have here for phase modulator, the deviation sensitivity is given by K and the unit is radian per volts, okay, radian per voltage, and it is given by the change in phase, okay, with respect to the change in the amplitude. So change in the amplitude, that is your delta V, okay, or the magnitude of your input signal. So for frequency modulation, it is given by K1 with a unit of radian per second per volt, okay? So radian per second per volt or radian volt second, okay? So this is the change in the frequency. So omega is 2 pi f. So change in frequency with respect to change in voltage or the amplitude, okay? So for phase modulation is the first integral of your frequency modulation. So that is how they are related with each other. So for PM, which is your theta t, that is equivalent to the first integral of the frequency modulation, which is the derivative. So frequency is the derivative of your theta t. So that is given by, so this is your sensitivity, okay, so deviation. So we have K1, Vm, T, so K1 is for Fm, so getting the first derivative, that is given by K1, the integral of Vm T dt. Okay, so substituting the modulating signal, so modulating signal is Vm cosine omega t into the equation, so it will become Vc cosine of omega ct plus theta t. So Vc cosine of omega ct, okay, plus Kvm. We have your Kvm cosine of omega t. So you have to remember this, class. So you have to take note of the formulas that we are using. Okay? So this is your for phase modulation. For Fm, it is given by Vc cosine of omega ct, then the integral of theta t theta prime t. Okay, so substituting Vc cosine of omega ct plus integral of K1. So substituting our PM here. So K1, our FM, K1 VMT. So this is the equivalent for that. So Vc cosine of omega ct plus K1 integral of Vm. So constant yung K1, ilalabas natin. Vm cosine of omega mt dt. So Vc cosine of omega ct plus K1 Vm all over omega m sine omega mt. So with respect to the M here stands for the modulating signals, while your C here stands for your carrier signals. Okay? Okay, so this table shows the summary for the equations for phase and frequency modulated carriers. So this is their modulating signal and this is the angle modulated waveform. So for phase modulation, okay, our modulating signal is VMT. For frequency modulation, our modulating signal is VMT also. Okay, so for phase, we can have Vm cosine omega mt. So for frequency, we can have Vm cosine omega mt. Okay, so it can either be a sine wave or a cosine wave. So for the angle modulated waveform, so for phase, it is given by Vc cosine omega ct plus Kvm. Okay, so K is the deviation sensitivity for phase modulation. Likewise, also here, this is for phase modulation. Okay, so for frequency, we have K1. K1 is your frequency sensitive deviation sensitivity for frequency modulation. Okay, so your modulating signal can either be sinusoidal waveform or it can also be a cosine waveform. Okay, so the figure illustrates both frequency and phase modulation of a sinusoidal carrier by a single frequency modulating signal. So this is somewhat identical except for their time relationship. Okay, so as you can see, what will be the difference between frequency modulated wave and the phase modulated wave. Okay, so we have here the unmodulated carrier. Look at the waveform. So usually carrier is the one which has higher frequency. Okay, so our modulating signal is the one which has lower frequency. So we have the in this case no modulation. So therefore what you can see is just the carrier. Okay, both for the FM and the PM here. Though we have here your zero slope, we have the maximums. This is the maximum slope, zero crossing. Okay, so maximum deviation and following. Okay, so what is the difference between the frequency modulated and the phase modulated waveform? Okay, so let us illustrate. Okay, so for FM or for frequency modulation, the instantaneous frequency is proportional to the modulating signal. Okay, frequency deviation is at maximum at the positive and negative peaks, rest at zero crossing. So as you can see for FM, okay, so at the maximum slope, this represents low frequency. At the lowest peak here, lower peak here, this corresponds to a high frequency. So what do we mean by that? The highest for the highest and for the lowest peak, there you can see the lowest and the highest frequency deviation. Okay? So when you are not at the highest or at its lower peak, you have the constant value. Okay, so the highest frequency change occurs at the peak of the modulating signal. So for PM, as you can see, the frequency deviation is maximum at zero crossing. Okay, so at zero crossing, like this one, it has a maximum. Another zero, it has the minimum. Another zero, it has the maximum. And when you have here another zero, we have here the minimum. So you can see the difference. As you can see, there is no change in the amplitude, right? So there is just a change in the frequency of the waveform. So for FM, you can see the lowest and the highest frequency. So lower frequency corresponds to few cycles, high frequency corresponds to many cycles. So the lowest and the highest frequency occurs at the maximum and its minimum peak, or vice versa. While for PM, you can see that the maximum and the minimum occurs at the zero crossing portion. Okay, so while it is constant at the maximum and the minimum, here it is higher at the maximum and the minimum, and it is constant at the peak and it rests at zero crossing. So that is the main difference between the frequency and the phase modulated waveform. So for FM, the maximum frequency deviation or the change in the carrier frequency occurs during the maximum positive and negative peaks of the modulating signal. For PM, the maximum frequency deviation occurs during the zero crossings of the modulating signal. Okay, so both for FM and PM, the rate at which the frequency changes occur is equal to the modulating signal frequency. So it is the modulating signal frequency that dictates, okay, the rate at which the frequency changes. So just like in AM, it is also the amplitude of the modulating signal that determines the envelope of your AM signal. Okay, so it changes the amplitude of the carrier signal. So the modulating signal changes the amplitude. However, here it is the frequency that is being changed, but still by the modulating signal frequency. So with frequency modulation, the instantaneous frequency is proportional to the modulating signal, and the instantaneous phase is proportional to the first time integral of the modulating signal. So for phase modulation, on the other hand, the instantaneous phase is proportional to the modulating signal, and the instantaneous frequency is proportional to the first time derivative or the waveform slope of the modulating signal. Okay, so we have here phase deviation and modulation index. So for general format, we have a general format here. We have VC cosine omega CT plus M cosine omega MT. So your M cosine omega MT here is the instantaneous phase deviation. Okay, or our omega T. Okay, so if you will remember our first formula, so this is your omega T, or theta T rather. M is the peak phase deviation, okay, in radians for phase modulated carrier. Okay, modulation, this is also the modulation index or the index of modulation. Okay, so M cosine omega MT is the instantaneous phase deviation, while M is the modulation index. Okay, so for PM, let us define our modulation index. So one primary difference between FM and PM is the way in which the modulation index is being defined. So let us define the difference. So for PM or modulation or for phase modulation, M or the modulation index is proportional to the amplitude of the modulating signal, and this is independent of its frequency. Okay, so M is given by kVm, and this is in terms of radians. M is the modulation index, and peak phase deviation theta, delta theta, okay, in terms of radians. So K, as you remember, is the deviation sensitivity, that is in radians per volts. Vm, that is the modulating signal amplitude, that is in terms of, that is also in terms of volts. Okay, so therefore, if you're going to get the unit for that, that is equivalent to K is radian. K is equal to radians per volt times Vm is volts, so it will be cancelled. So the unit for the modulation index for PM is radians. So in AM, the modulating index or the modulation index has no unit, but for PM, the unit is radians. Okay? Okay, so we can volts. So the unit is radians. Okay, so let us remember the PM equation. So put this in your mind. We have VC cosine omega CT, K Vm cosine omega CT. Okay, so VC cosine omega CT, or the change or the phase deviation cosine of omega MT, or cosine MT, M cosine omega MT. So these are just the same. Okay, so it is represented by the frequency. This is represented by the deviation coefficient. So this is represented by the phase deviation, and this is represented by the modulating coefficient, or the modulation coefficient. Okay, so there are different representations, but they are just the same. So let us now go to FM. Okay, so the modulation index for FM is directly proportional to the amplitude of the modulating signal and is inversely proportional to the frequency of the modulating signal. Okay, so M is equal to K1. So this is your deviation coefficient for FM, K1. It is directly proportional to the amplitude. So this is your amplitude, directly proportional to the amplitude, and inversely proportional to the frequency. So frequency is this one, represented by omega m. Okay, because omega m is 2 pi fm. So therefore, it is related to frequency. So the modulation index in this case is unitless. Why? Our deviation sensitivity Our deviation sensitivity is radian per voltage second, okay, multiplied by volts, okay, divided by radians per second. So volts will cancel out, radians will cancel out, seconds will cancel out, giving our modulation index for FM to be unitless. Okay, so that is for FM. Okay, so this shows why our modulation coefficient for FM is unitless. Okay, so radians will be cancelled out, volts will be cancelled out, seconds will be cancelled out, so it is unitless. Okay, it can also be represented in hertz per volt. So our M is equivalent to K1. So K1 is hertz per volt. And then our FM is in terms of hertz. So likewise, volts will be cancelled out, hertz will be cancelled out, leaving our modulation coefficient for FM to be unitless. Okay, so it is used only to describe the modulation coefficient for FM is used only to describe the depth of modulation achieved for a modulating signal with a given peak amplitude and radian frequency. Okay, so deviation sensitivity can also be expressed in terms of hertz per volt, like in this example. Okay, so I will end first the video here, and I will be uploading another video for the continuation of our angle modulation. Okay, so goodbye for now and wait for the following video. Okay, bye.